Now we're going to talk about some volumes of revolution. What this means is we're going to take different functions and we're going to revolve them around the x-axis or the y-axis or some line parallel to those axes and figure out what solid we've created and get its volume. So the first method we're going to use is called the disk method. So the first thing we need to look at is disks in the first place. So we've got on your notes, you'll see at the top of I think it's the third page, it says Day 2, Volumes of Solids of Revolution, the disk method. And it has a picture of a rectangle at the top, and it's revolving this rectangle around the x-axis. If you revolve a rectangle around the x-axis, you have this narrow cylinder. And just like we've talked about over and over again, we take these little bitty, narrow, thin pieces. We used areas before, and now we're using volumes. And we add them all up using integration, and we'll get the total volume. So what we need to realize is when we draw these disks, we've got a little height of our disk, or the width of the disk, whatever you want to call it, and then it has this radius from the axis of revolution out to the edge is some radius. And you know that the volume of a cylinder is the area of the base times the height. So the volume of a cylinder is the area of this base times the height. So this is going to give you your volume of your disk. So how does that help us? Well, when you have the disk method, if you have a whole bunch of little disks along the axes, then you can take this area and add it up along your part that you're taking the volume of. So if you have from A to B and you've got some function and you take a lot of little cylinders around it, then you can find the volume of the whole solid, whatever that happens to be. Say we draw a function in like this, and we rotate it around the x-axis. So we end up with this sort of trumpet-looking solid. If we take the cylinders, then we can integrate from A to B the volume of each individual little piece and get the total volume. So you've got a couple of formulas there in the middle where it shows you a horizontal axis of revolution and a vertical axis of revolution, and that those formulas are there for you if you want, but you need to remember that memorizing those formulas isn't necessarily going to help you. If you understand them, then you won't really need to have them memorized in the first place. So let's look at this first example. It says, draw an appropriate rectangular strip and find the volume of a solid formed by revolving the region y equals 4 minus x squared along about the x-axis. So on all of these, your number one first step is to draw a picture. If you don't draw a picture, it's going to be very confusing for you. So our function is y equals 4 minus x squared. So if we draw that in here, we just want the piece that goes to the x-axis. So this is all we have here. We're going to rotate it about the x-axis, so that means it's going to come in here, go down just like this, and be this solid. So what we need is a disk. So we draw in our disk so we can see what we're doing. It is important to draw in that disk every time. That way you can see, okay, my little width is indeed dx because it's along the x-axis, it's an x width. And what's my radius? Well, my radius goes out to the function. So my radius is going to be 4 minus x squared. And if you don't draw in your picture, sometimes you'll end up doing your variables backwards because you won't see exactly where you're revolving. So make sure you draw a picture. Alright, so we want the volume of this solid, so it's kind of an egg-shaped solid here. And we're going from x equals, we're on the x-axis, we're using dx, so we use our x limits here. We are going from -2 to 2, because that's where this function hits the axis, and the area of each of these, or the volume of each of these little disks is pi r squared, and then times the height of the cylinders, the little disks, is dx. So we have this volume here. We're not going to calculate that out right now, but we've got pi r squared dx. So we're going to take each little cylinder and add them all up. You can calculate that out by foiling it out and doing individual steps pretty easily. Alright, now let's look on the back of that page and try another one. What if we have y equals the square root of 16 minus x squared, and we want to revolve it around the y-axis. Alright, so what does that look like? Well, 16 minus x squared, so that means it's going 1, 2, 3, 4. It looks something like this. And we're going to revolve it around the y-axis, so we're going this way around the y-axis, which gives us a dome shape. So we draw in our little disc here, and remember, the disc has to be perpendicular to the axis of revolution, always. So our disc needs to be with a dy this time, because our little width here, our little height of the cylinder, is on the y-axis. And our radius needs to be out here, but notice we're using dy. So what we need to do is solve this for x, so that we have it in terms of y. So if you solve this for x, you get that x equals the square root of 16 minus y squared. So that's our radius. So then when we set that up, we have the integral. We're going from 0 to 4, so that we can revolve it around the axis. If you go from -4 to 4, you'll end up with twice as much volume. So you don't want all of that. You just want it revolved around one time, so don't overlap. And then we have pi r squared h. So we're taking each of the little discs, each of the little discs here, and adding them up. So that gives us the integral from 0 to 4 of pi times 16 minus y squared dy. So that's pi times 16y minus y cubed over 3, evaluated from 0 to 4, which gives us pi times 64 minus 64 over 3, which is 128 pi over 3 units cubed. Alright, so you can see that we can do it around the x-axis, as we did the first one, and then around the y-axis. But you also can do these problems around other lines as well. So let's look at the last example there on that page. It says, find the volume of solid generated by revolving the region bounded by the graphs of the equations xy equals 6, y equals 2, y equals 6, and x equals 6 about the indicated lines. Sketch the region formed and draw a representative rectangular strip, or draw your disk out is what it's saying. So we've got this region, and this is y equals 6 over x. If you want to graph that, and what it looks like is something like this. And then we've got the line y equals 2. So it comes in here like So hopefully you're drawing a straighter line than I am. 3, 4, 5, 6. And the line x equals 6. Okay, so we've got this shaded region here, and actually this picture is terrible. It's not really showing you the right thing. So let me adjust it a little here to make sure you can see what you need to. There. All right, so we've got this area here. And we're going to take this area, and the first part we're going to revolve it around the line x equals 6. So we're going to revolve it this way around this line x equals 6, which means we'll end up with a shape where it comes kind of over here. We get a disc like this. Remember, discs perpendicular to the axis of revolution. So what does this mean? Well, it means we're using dy because our width is the dy. And then we look at our radius. Now the radius is, we usually measure the radius in the part that's the original area. So here's our radius. And if you look at this, it's 6 minus, and then we've got to know what this function is in terms of y. So this function, if we solve it for x, we get 6 over y. So our radius is 6 minus 6 over y. So make sure you understand that. All right, so to set up, if we're revolving around that line x equals 6, we're setting up our integral. We're going from y equals 2 to y equals 6, because that's what our bounds are there. And then we just do pi r squared h. Pi r squared h. And I'm going to trust that you can multiply that out and figure that out. You'll get approximately 241.588 cubic units. So we can revolve it around lines other than the axes. What if we want to revolve it around the line y equals 6? So we're going to do this one. This is harder to see, sorry. Which that means is we end up with this extra stuff up here. And you can't really see that as well, but the disc will look something like this. And we're going to measure our radius here from the center out to, oh, sorry, I'm confusing myself with the blue part. It'll go down to here, of course. And the radius will go all the way out here. Now, you see immediately that you have a little bit of a difficulty because our radius is going to be something different in this part here than it is in this part here, because we got all these little discs moving up and down there. So what we've got to do is take that into consideration and find this point here. So this point where they meet is at x equals 3. So what we're going to do is set up our integrals, because from 1 to 3, which this hits at x equals 1, from 1 to 3, our radius is going to be 6. This line up here is 6 minus this function here. So that's 6 over x. And from 3 to 6, our radius is constant. It's just 4 because we're going from the line 6 to the line 2. So we just have to split it up. So we do the same thing though. We go from 1 to 3 of pi r squared h plus from 3 to 6 of pi r squared h. And again, I trust you can calculate that all out, and you get 203.89 units cubed. So you can revolve these around any of these axes. The main issue you have to look at is what's my radius of these disks. And if you don't draw you a picture, you're going to have trouble finding it. So make sure you draw you a picture and that you label your picture and figure out whether you're using dx or dy, and figure out what those radii are. Don't just assume it's straight up the function. Look at the picture and see what's happening. Make sure you've read this section. If you read it before, that's great. Read it again. Make sure you've gone over this, and we'll do some practice problems in class.